So in this chapter, we will study about the stiffness methods of grids. Usually we study the stiffness method of analysis for the frames in 2D plane. This grid set will come in 3D plane. So far in this text, we have been almost exclusively concerned with the analysis of two-dimensional frames set in the vertical axis plane. I mean horizontal x-axis, vertical z-axis. In that vertical axis plane only, all real structures are of course three-dimensional. Vertical axis z-axis, horizontal x in this plane, and out of plane this plane is y-axis. That is, all real structures are three-dimensional, of course. However, most structural frames, particularly those for the multi-story structures, are resolved into series of subframes which are set in this two-dimensional axis plane. This means that most of the multi-story structures we can make 2D frames, and other direction these frames will be like a repetitive or translated. So that's the reason if we study for this critical two-dimensional planes, that would be applicable for other two-dimensional planes in the y-axis lateral direction. Consequently, this academic emphasis is genuinely a reflection of the day-to-day activities of structural engineer. Occasionally, though, it is necessary to design the structure capable of carrying load normal to the structural plane that is defined as a grid. The same basic theoretical approach is employed in the stiffness method as well. In the next slides, we could see in detail about these grids, how the analysis could be made. In this slide, we could see that you just notice this ABC bent. A is fixed and BC are horizontal member, and load is applied at C, load W. We have studied the analysis of cantilever bent ABC loaded at C from a number of different aspects. These things we have studied in the previous chapter 7 in number of different aspects about this bent cantilever analysis. Suppose if we introduce an additional member CD, you could see this is the CD member. If we introduce an additional member CD in the third dimension, in Y dimension, you can see here Y. In the third dimension Y, if we introduce this additional member CD, a new stress resultant is introduced. New stress resultant is nothing but the torsion in the member BC. If we apply load here, this load into the CD distance span, it will generate a torsion in this member BC. That's why this new stress resultant is introduced. That stress result is nothing but torsion in the member BC. This is the most significant difference between the plane frames and grids. If you have this kind of plane frames, you will not have any torsion on this member, but in this grid one, you will have the torsion effect. This is the most significant difference between the plane frames and grids. The torsional stiffness of the member. This member BC's torsional stiffness is normally included in the resistance of the member in grid structures. Consequently, there is a rotation about longitudinal axis. In the BC member, the longitudinal axis it will go like this along this x direction. About that axis, the BC will rotate. That is due to the torsional effects. Here you could see the stress resultants: axial, shear, bending, and torsion are identified in relation to the member local axis rather than the global axis. It means that all these torsion, bending, axial, and shear, torsional stress, all these are identified in relation to the member local axis. This is the member local axis, x-axis longitudinal direction, y-axis lateral direction, z is in the vertical direction. This is the member local axis. This is how we identify all the stress resultants in the member local axis rather than the global axis. The member axis will be identified with lowercase symbols. You could see here x, small y. These are the lower cases used to identify the axis, member axis. There is a bending moment about major axis my. Here you can see these members. This is the axis y. About this axis y, there is a moment because of this load at d about this local y-axis. There is a moment my. This is same as the bending moment analysis of the plane frames. If you see in the BC member also, if you apply this one here, there will be a moment BC. Here you could see this moment BC is there. This is same as the plane frame analysis what we have done earlier. There is a resultant shear in the Z direction. Here you can see this is the resultant shear in the Z direction. Okay, there is a resultant shear Z direction, and the new load effect, that the torsion about the x-axis mx in the member BC. Okay, now we will study the qualitative analysis of this cantilever bend frame ABCD. Vertical load at D produces a bending moment at C my, that is about the member y-axis. In addition, there must be an upward shear force, okay, at C in the member z-axis resisting the downward load at D. This downward load at D is resisted by the z shear axis at C. Okay, this shear force in CD, this shear force in CD is equal to the load W. That shear force is transmitted to the member BC as a point load at C, which in turn produces the bending moment about the y-axis of this member BC. That is, the produces bending moment like this about this member BC. The shear force is transmitter constant in members CD and BC. Whatever the shear force is coming here, the same shear force is registered here. That shear force is go to the BC also. So shear force is becoming like this. That is constant. Here you could see the shear diagram. Here you can see the shear that is constant in the CD as well as BC. The bending moment in the CD at C my is resisted by torsion in the BC, because this moment is this load is applied here, so it will produce a moment. That moment is resisted by the BC, that is by torsion, which is constant throughout the member. If you see this load and this distance, that is constant for this member BC. This perpendicular distance same. That's why the torsion is constant at here. Here you could see this at the joint B. The moment about y-axis in member BC my, this moment is transmitted into the column about its y-axis. This y-axis like this, that is resisted by like this y-axis. The shear force at B is resisted as an axial force by the axial force in AB. The torsion in BC is resisted by the bending moment in column about z-axis. This is like this. This mz is resisting the torsion in the member BC about its z-axis of that member. This is how it's shown here. Here you could see this is the y-axis, this is the y-axis, this is the column. Its column's y-axis is like this and z-axis is like this. So about this z-axis only the torsion is resisted. Okay, here you can see the torsion also. This figure 7 shows the final shear force. The shear force is constant like this. Here it will act like axial force. The final shear force and the axial diagram. There are no axial forces in BC or CD since the loading is normal to these members. For these two members, loading is normal. This member is like this, load is like this. So these two members, its load is normal, so there is no axial direction force, there is no axial force in this either BC or CD. And if we take this moment reactions at A, M, Y, and M is a moment in the column AB. There is no torsion moment for this column AB since the load is parallel to the longitudinal axis of the member AB. For there to be a torsion in this member, there should be a force in this lateral direction. For that to be a torsion member AB, there would have to be a load at angle to the global z-axis. Over this global z-axis, there should be a load. So here it is not the case, so there is no torsion here. Torsion is only on BC member. Let us look at this picture here. Load is applied at this D, right? So the deflector shape, we can see it. Here it is fixed, so there is no translation or rotation. So it will become like this. Because of this load at W here, it will move in this horizontal axis direction as well as in this Y direction also. So B will be both positive Y and positive X, it will move. Once it is moved, the same amount of movement for the C and D in this x-axis it will happen. At the same time, this AB vertical height it will not change, so it is like this. But however, C it will go down because of this vertical load, so it goes down. That means X and Z, but in the same plane because there is no lateral load. So BC it will deflect in the same plane. BC. Then from the C and D also it will be in the same plane, but D will go further down because of this load. So there is a tension here throughout. It's a single curvature. This also single curvature, and single curvature. That's why in the moment is like this and like this and like this. Here the deflector shape may be built upon by consideration of the resulting extension of the fibers in the bending tension from a vertical from a vertical arch A, the bending tension will deflect the column AB in the positive direction of both X and Y axis. Since there is no bending about Z axis, the BC will not rotate. Z axis BC or rotation about AB, the point C will deflect directly downwards in the plane parallel to XZ plane. So this will directly bend in the XZ plane only. Similarly, there is no horizontal deflection at point D other than that introduced by the horizontal deflection of point B. So in C also to move that much. Here you can see this is the STAD model. Here the load is applied here. We can see the bending moment, how it looks like, and the deflection also we can look at like this, how it is there like that. This is the analysis from the STAD Pro and small example it was made to explain to show the details, illustrate the details, how it bends for each and every member. Here you could see the same frame grid members and apply that load here, set 10 kilonewton, and this is the deflect shape of that frame. It is moving downwards here, and it is moving both in X and lateral directions, and vertically it will not move because this axial deflection we are not taking into consideration, and it will move bend it at the same plane, then it further deflects there.